And this?
Cauliflower.
Okay. Okay. So possibly this. So two of these four looks like cauliflower, and rest two looks like cotton, right?
Yes.
Okay. Actually, four are cauliflower. Okay. So and I'll tell you that why rest two looks like cotton, and maybe now it will not look like cotton. So focus a bit. How it looks like now? This looks different now. I'm trying to focus the camera. Slide focusing is possible in this camera. So because I see my screen much smaller than you do, so I'm not able to see the focus. So how does it look like? Okay, now I can actually lift it a bit. Okay. So what is this? Huh?
Cauliflower.
Okay. A very small part of a cauliflower. That's why you see that it's on the tip of a pen. Right? You see? This is a little larger piece of cauliflower. This is even larger. And this is the whole cauliflower. Now, if I give you the all individual small pictures of part of a cauliflower, and I do not give you this pen, I do not show the pen along with this cauliflower. So how easy it will be for you to tell whether it's a part of a cauliflower or the entire cauliflower? So you looked at this picture, huh?
There's no reference.
Yeah, it is difficult. And why? Why it's difficult?
So the pen gives reference like a standard, which we
Pen
can.
gives you the absolute size of the part of the cauliflower. If someone gives you the absolute scale, you know that this is not the whole cauliflower because you have the entire idea that how a cauliflower, what is the size of a cauliflower. Now, where is my this one note here? Yeah, got it. Okay, so this one note is visible. This
Yes,
one note is visible to all.
Yes, sir.
Yes, sir. Okay, good. So now, so say this is the cauliflower, and this is a small part of cauliflower. Now, if I scale this picture with this length, so this is another little larger part of cauliflower. Now I enlarge this picture in a length scale. See, this is length absolute centimeter scale. Okay. So if I draw this centimeter scale to the cauliflower, this is the entire cauliflower. This is small part of cauliflower. This is centimeter scale. Now instead of centimeter scale, suppose I devise a scale which is this length is 1 unit. Okay. So this big cauliflower will span from 0 to 1, 0 to 1, and it will look like this. Even the smaller one, because now this unit is this, 1 unit. So for this cauliflower, the length unit is different. So in this unit, this cauliflower also looked like right? So do you agree to that?
Yes, sir. Yes, sir.
So many natural objects show this feature that if you scale it appropriately, many different objects or part of the object looks exactly the same. So there are many names to this behavior. Some call it fractal behavior. For our case, we call it self-similar. Or scaling behavior. This is part of nature. Nature has this feature that if you take an object and scale it appropriately, different part of these objects looks the same. So just understand this thing clearly, that how we scale, we get an appropriate length scale for that object and plot or draw or take picture of this object in that scale. See, if what I was doing is that I was taking this small part of this cauliflower. I was taking this small part of this cauliflower. Close to if I keep it here, and if I keep this to here, so this looks like this. But what I was doing is that I was taking this closer to the camera, and this was far. So that's why it was looking like cotton, because camera was not able to focus to that. But if you can look at this with proper focusing, it's very difficult to see the difference between these two. And now you can compare this with the picture I have drawn, and you see that this is called similarity behavior or self-similarity or scaling behavior. We need this today. So that means different objects, different plots, if they are scaled in a proper way, so they overlap over each other. Is that clear? Any question?
This should only starts looking similar. So this should only starts looking similar.
This applies to things which look similar when scaled.
Yes, yes.
Okay. If you scale it, it should look exactly same. Or yeah, you are correct that they should look similar. Since part of gobi is looks like gobi, but part of a papaya, if you cut it, it doesn't look like entire whole papaya. So yeah, so not all objects show this feature. Some and many objects in nature, many mathematical functions in the nature, they show this scaling feature. That if you scale it appropriately, different functions, they merge together. So that is the whole idea. So now let us get back to today's business. Get rid of this gobi and let us start our business today. Okay. hold on. Today we will discuss conduction in semi-infinite solid. So semi-infinite solids are solids which are extended in one direction to infinite extent. See, for example, the earth. For all practical purpose, the depth goes till infinity. So this is the z coordinate, and z coordinate goes to 0 to infinity. So it's called semi-infinite domain. This is called semi-infinite domain. That what semi, because the infinite domain spans from minus infinity to plus infinity. It's half of that. It's from 0 to infinity. That's why it's a semi-infinite domain. So we'll discuss today is conduction in semi-infinite solid. So the problem is that at t equals to 0, the entire solid was at a temperature T0. Everywhere the temperature was T0. Now at time t equals to 0, suddenly we expose this surface to a temperature Ta. And we ask how the temperature in this solid will change with space and time. Okay, so we'll do it in Cartesian coordinate because it's easier. So we can think not this as any other coordinate system. This is just a slab. So it's a slab, but it's infinitely thick. So that's the Cartesian system. Now I want you to draw qualitatively how the temperature in the slab will change with time. And I want you to show it to me. Ready? Snehbandhu. So this is at what time? See, this is you have to plot as a function of space and time, right? So you have to make it a parametric plot. So you have to plot at different times.
Yes, sir.
Yes, sir. Got it? Plot at different times just on the same plot, so that we can see the time t1 one plot, time t2 another plot, another line. So different time, draw different lines. There's a typical it's called parametric plot. Who else is ready? Whatever you got, so you can show it. Do not bother too much about your image to others. Who else is ready? Abhishek Purohit, what is your plot?
Sir, I am still trying, sir.
Okay, okay, all right. Just use your intuition. Don't worry too much about uh, what you learned and this and that. So no need to apply any hi-fi knowledge. Just use your intuition that if suddenly something is exposed one surface to a temperature, how the thing will respond.
So flash.
Ha.
Sir, something like this. Where the plot T versus X and the different lines in different times.
Okay, okay. Something is missing at x equals z equals to 0. Just think a little bit more in that direction. Huh?
Okay, sir.
Otherwise, it's okay. Okay, z equals to 0, something is wrong. Let me see some more. See, this surface is always at TA. Surface we always maintain at TA. So this at z equals to 0, temperature is always TA. Snehavandu, you could correct, and do you have your plot ready now? Sharon Havda.
So actually, I'm not, because we have to space.
Temperature is sign up as a function of space and time. Yes.
So it should be a
Yeah, but there's a 3D, that's a 3D XYZ coordinate temperature as a function of space and time is a 3D, but you can write it as a parametric plot. So I thought you are familiar with these parametric plots, but let me then draw some one here. Okay, so let me take this weight. Now, you see this at time t equals to 0 plus, you suddenly make this TA. Say, let me call this as temperature axis, and this is z axis. And at time t equals to 0 plus, at time t equals to 0 plus, this temperature has reached set to TA. But it didn't get time. The other part of this solid is still at a temperature of T0. say TA is 100 degrees centigrade and this T0 is 0 degree centigrade. So other part of this needs some time for heat to diffuse and come here to conduction. So at T equals to 0, it's like a step function. So this is the temperature profile at T equals to 0. So this at T equals to 0. Now, suppose T equals to, say T equals to 10 seconds. Say T equals to 10 seconds. So T equals to 10 seconds, it has got heated up till certain distance, say up to this, a little heat up occurred. But beyond this distance, it still fall to 0 degree. This is at T equals to 10 seconds. Now, let us go to say T equals to another time. So this is T equals to say 30 seconds. Another time. Say this is T equals to 40 seconds. Alright? So this is how this profile will quantitatively look like. So do you agree to that?
Sir, this is the air above the ground get heated up or cooled down.
So above the ground. So above the ground you are flowing a large quantity of fluid at TA. So there will be no change in temperature here whatsoever. So this is always maintained at a temperature of TA. No change in anything above Z equals to 0. Okay, anybody has any question on that? It's clear? Aditya Agarwal.
Yes, sir.
Yes, sir.
It is clear.
Yes. Okay. Let me see. Somil Varilya.
Yes, sir.
Yes, sir.
Clear to you?
Yes, sir.
Yes, sir.
Yes, Jain.
Yes, sir.
Yes, sir.
Sai Nanda. Yes, Jain, it's clear to you?
Yes, sir.
Yes, sir.
Okay. How about Sai Nanda? Sai Nanda, what happened? Okay. Samira Yasmin?
Yes, sir.
Yes, sir.
Okay, very good. So now, what I want you to think, this pen. So let me just extend this. Okay, so these are the temperature profiles at different times. If I tell you that this material has a thermal diffusivity of alpha, can you give an approximate estimate of this length scale? Or let us call it characteristic length Z characteristic. See, this is dependent on time, right? So it goes, the temperature profile goes till certain distance depending on time, and the longer you wait, it will go more and more. It will penetrate more and more. Rather, it penetrates. Z characteristic is some kind of approximation of penetration depth. So if I give you alpha, a value of alpha, and give you time, value of time, so 30 seconds, 40 seconds. So can you give me a rough estimate of this characteristic length or penetration depth?
Under root alpha.
Under root alpha t. Because alpha is, you know, that centimeter square per second or meter square per second. So let us stay in the SI system. Alpha is meter square per second. So alpha t is in second. So alpha t gives you meter square. So square root of alpha t give you the meter. That's the characteristic depth, or we can call it penetration depth, approximate. Just be convinced that this is an estimate of penetration depth, square root of alpha t. So, have any question? Please feel free to ask. All ideas are built on the previous ideas. So, the characteristic X we did for the this thing that you have to. If you remember and understand this correctly, so this you will be able to understand that penetration depth is square root alpha t. Now, the last part of this idea, rest is little bit algebra. Now, if we want to plot this, instead of z, we plot in terms of z divided by square root of alpha t. The temperature is same temperature here. Huh? So, at t equals to 10 seconds, so this was our green plot. T equals to 10 seconds. Now this z was spanning from here to here. So this is the span of z. So this is the span of z. So this is the span of z for this case. Now we scale it. We scale it by alpha t, or you can call it non-dimensionalized z. So it will span from 0 to 1, may not be exactly 1, but approximately 1. And this t will reach from 100 degrees centigrade to 0 degree centigrade in approximately this length. So this plot will look like this. Now if I plot, this is our t equals to 10 seconds. Now if we plot, I think we took this one, this one. Now if we plot t equals to 30 seconds. So it was, can it go something like this, or should it end somewhere around 1 again? Huh?
Around 1.
Around 1, because we have scaled it. Okay. So z naught may be more, but because t is more, square root of alpha t is also more, so the ratio more or less remains towards 1. So this plot will look like this. Now if I go to the next, so maybe this one, or this one, okay. So now we go to t equals to 30 seconds. Again this plot will go like this, just like our cauliflower. गोभी का एक छोटा फूल बड़ा फूल जो भी पकड़ लो, so those look same, and it turns out those are actually exactly the same curve. Okay, so this is, we have scaled the plot, and as a result the temperature plots at different t collapses into a single curve. So if you talk about experimental data, it approximately collapses, but if you talk about the differential equation, because this behavior is observed and occurs in the system, these all plots collapses exactly to a single curve. So that is what happens. So scaling behavior, this is observed for this system, and so this differential equation also obeys this scaling behavior exactly. So once you scale z by square root of alpha t, all these plots collapses into a single plot. Digest this fact. This is the most crucial part of what we will be going to discuss today. So if you understand all we discussed this far, so there is nothing else to stop you from mastering this particular topic.
Why it should same but not.
It becomes exact because this kind of, in terms of mathematics, if we do this variable transformation, you see that this is basically a variable transformation. If we do the variable transformation, the partial differential equation reduces to an ordinary differential equation. So we'll see that. Mathematically, that's why all these plots collapse, because with this variable transformation, this t is a function of z and t in this particular combination. There is no independent variation with z or independent variation with t. That is why this collapses exactly. I think it will work once we start writing the equation and make this transformation, it will be clear. But for as on experimental data, such kind of collapses are observed, and those are exact for many systems and approximate for a lot of other systems.
Okay, sir.
Okay, so now what you do is that you write the transient conduction equation. One dimensional transient means one space dimension, and the boundary conditions for this equation on your notebook and show it to me. You can look at my notes that I sent and go to the first chapter itself. So where we took the cubic element and derived this transient equation, set the source term to 0, make the other coordinates 0, velocity 0, you will get the transient equation in Cartesian coordinate. Write it to your notebook. Then write the boundary conditions. First, show me the equation. Boundary conditions I can see. If you are ready with the equation, show it to me. Swarup Ranjan? Swarup Ranjan Mandal. See, U, there will not be any U because there is no velocity, it's a conduction, pure conduction. Okay, and there will be no source term either.
So this is box
बॉक्स का बगल में वो कुछ क्यू कुछ है उसको हटाओ, ठीक है, और u is 0, so there will be no u, that term will also be there, otherwise it's okay. Now just write down the boundary conditions, ठीक है, good, very good. Anyone else want to show? Advita Roy.
Yes, sir.
Show me the equation. Yeah. Boundary condition, just to thoda sa, just to pull it little away. Yeah. No, nazdik lao. This is better. At t equals to 0, t equals to t0, all x. Okay. At x equals to 0, t equals to t0, all t greater than 0. Okay. Write down the third condition.
Yes.
We need two x conditions and one initial condition. Okay, good. So, anyone else?
This is the
At x equals to infinity, t equals to t0, all t. Okay, your 0 and a looks same, so I suppose that one is a. Okay, alright, good. So now, we have these conditions. The differential equation is partial t equals to alpha z2 at z equals to 0, t equals to t0, all t greater than 0, at z equals to infinity, t equals to, this is t equals to ta, and t equals to t0 for all t, at t equals to 0, t equals to t0 for all z. Okay, so this is the equation and boundary conditions. Okay, now although you see that there is no length scale without involving t, so we cannot non-dimensionalize t and z separately. We can do this by combining this, as we have seen, but separately we cannot have non-dimensionalized t and z. So we cannot do that, but we can non-dimensionalize this t by using theta. So we can define theta equals to t minus ta and t0 minus ta. And you can see that this transformation is straightforward. So this becomes partial theta partial t equals to alpha, second derivative of theta with respect to second derivative of z, and at z equals to 0, t equals to ta, that means theta equals to 0. At z equals to infinity, theta equals to 1. At t equals to 0, theta equals to 1. So these are the conditions, okay, in terms of theta. So now let us do this transformation. So although I wrote it here at z hat, typically this variable is defined as eta. So we call it eta. So we will call eta equals to z divided by square root of 4 alpha t. Why the 4 is here? Actually it will cancel with some 2 somewhere coming later. So you can or cannot, but most of the analysis people use this 4 because it gives you little ease later, algebraic ease, nothing more. There is no fundamental requirement for this 4. So this is eta. So now, as I said that this partial differential equation collapses to a ordinary differential equation if we make this variable transformation. This is also called a method of combination of variables for solving partial differential equation. This works only when this similarity behavior is embedded in the system, otherwise it will not. So z eta equals to z. Now our next task is to transfer this equation and boundary condition in terms of eta. Okay. So first we have to write all these derivatives, we have to replace in terms of eta and also the boundary conditions. We can see that at z equals to 0, eta goes to 0. At t tends to 0, eta tends to infinity. So z tends to 0, eta tends to infinity. You can see that these two boundary conditions actually merge into a single. So that is that gives us some hope. That's good for us actually, because we said that this will become an ordinary differential equation. It will remain second order. So we need two boundary conditions, and if we had these different conditions for eta here, that would give us trouble. So at least with that trouble we don't have. So keep that in mind. You may not understand it entirely at this point, but keep that in mind. Okay. So we also need the transformation of the derivatives. So del by del t, and we also say that we assume theta as a function of eta. Theta, instead of being a function of z and t, so
Sir, can you explain the third boundary?
yeah. So just hold on. I'll repeat this because a lot of things going very fast here now. So we said that although eta is a function of z and t, but if we combine z and t this way in eta, we will be able to write eta, this theta. Oops. Although theta is a function of z and t, so if we combine theta in this way, theta can be written as a function of eta alone, where eta is defined by this. Now I want you to address your concerns. Tell me, what's that?
Sir, in third boundary, z tends to 0. Like
not z tends to 0, z tends to infinity. Okay? It's fine now?
yes, sir.
Okay. Alright. So we also assumed here, see this, as I said that this plot all collapses together, that is equivalent to the assumption or condition that t is a function of eta only, provided eta combines z and t in this some special way. So now let us see, transform the derivatives. So we can write del by del t equals to, or we can write del theta by del t equals to d theta over d eta del eta del t. So, and we can write Okay. So this we have written the derivatives in this term. Is this step clear?
Yes, sir.
Okay. So now from this definition of eta, let us get these terms. Del eta del t equals to t to the power minus half, that means minus half so let's put so equals to, just watch these steps very carefully because I don't have this written anywhere, and if I make small mistake here that will give trouble later. 4 alpha t to the power half यहाँ पे डालो minus half t to the power minus 1. So this becomes minus half, basically t to the power not half, so this is t inside. So this is minus half, this is eta, and t to the power minus 1 equals to minus eta by twice t. Okay, so that is del eta del t. Now let us see del eta del z is easier, is to 1 by square root of 4 alpha t. Okay, so now let us substitute these things in this equation. So del theta del t equals to d theta d eta del eta del t equals to alpha times d over d eta d theta d eta del eta del z okay, just substitution, nothing here. So now I substitute this derivatives. So del eta del t equals to negative of eta over twice t d theta d eta equals to alpha times d by d eta of d theta d eta. D eta dz is 1 by square root of 4 alpha t, and this is 1 by square root of 4 alpha t. So that gives minus eta over twice t d theta d eta alpha 1 over 4 alpha t, and we get here d2 theta d eta 2. So this t cancels, this alpha cancels, this 2 gives 2 here. So we get this second order ordinary differential equation with variable coefficient. So you see that had it been not obeying the scaling condition, we could not make this collapse. You see this T or Z didn't appear anywhere. They cancelled in some way. So they cancelled. So if this transformation was wrong, so this will not have this cancellation would not have occurred. So now what we get is that d2 theta d eta 2 plus twice eta d theta d eta equals to 0. So this is the ordinary differential equation showing the variation. And now we need to put the boundary conditions. You see that this boundary conditions actually collapses. So boundary conditions collapses to z equals to 0 means eta equals to 0 at eta equals to 0, theta equals to 0, at eta equals to infinity, theta equals to 1. Alright. So this is the equation and boundary condition. Okay, just carefully look at this. So this algebra is a little bit tedious, but it's okay. Sharon Holder. Gone. Sharon Maiti.
Yes, sir.
So is transformation clear to you?
Yes, sir.
Okay. Rahul Goldar. Varun Balakrishna.
Yes.
Is clear?
Yes, sir.
Okay. Varun Balakrishna. Now how do you solve this question? Have you seen this kind of equations?
Yes, sir.
Okay.
Take e square plus 2n of capital. What we did first, yeah.
This square thing will not be able to solve because that is for constant coefficient. This is a variable coefficient. Variable coefficient. So to solve this, we'll say this phi equals to, we'll do a little bit transformation, d theta d eta. So this equation then becomes d phi d eta plus twice eta phi. So that is variable separable. So that becomes d phi over phi equals to negative of 2 eta d eta. So if we integrate ln phi equals to twice eta square by 2 plus c, right? Yeah, so this is where this 2 will cancel. Okay, so this 4 that we were kept for so long is for this reason, that it will cancel with this 2. So then phi equals to e to the power minus eta square plus e to the power c. So we can write it as c1 e to the power, let's become very, okay. So from here we can write that phi equals to e to the power minus eta square plus c, or e to the power then plus c here. So e to the power c is a constant, so you can write it c1 e to the power minus eta square. You can write directly from the equation itself. Okay. So this is phi. Phi is d theta d eta equals to c1 e to the power minus eta square. So theta equals to c1 integration of e to the power minus eta square d eta plus c2. Okay, so solution is obtained. Now the second thing is that we have to evaluate c1 and c2. So if we see at eta equals to 0, theta equals to 0. So 0 equals to c1 d eta plus c2. So this becomes eta, and because eta equals to 0, this becomes 0. So basically c2 is 0. So we have used this boundary condition. So now we are left with this boundary condition. So we have theta equals to 1 equals to c1 limit eta tends to infinity integration of e to the power minus eta square d eta. Okay, so this will give us the value of c1. Everyone on the same page? Everyone is clear till now?
Condition.
How you
This boundary condition, theta equals to 1 you are asking, your voice was not coming clear.
so theta
Theta is equals
Break हो रहा है कभी कभी. Okay, so just write in the chat box. What I'm guessing is that theta equals to 1 is giving you some trouble, or theta equals to 0. Chat box में type करो एक बार. Theta equals to 0. Okay. Theta equals to 0 is for eta equals to 0. Okay, so the 0 equals to c1 integration of this. So if we just let me then do this in a little bit more steps. So we have, so we can write it in this way. So 0 equals to c1. We can also write limit eta tends to 0 integration e to the power minus eta square d eta plus c2. So we can also write this way, c2. So we have equation 1 and equation 2. So now we can solve these two. We can solve this say equation So now say let us go to equation 2 minus equation 1. So equation 2 minus equation 1, we get C1 limit at n tends to infinity, integration of e to the power minus eta square d eta minus limit at eta tends to 0, integration e to the power minus eta square d eta equals to 1. Okay. So from here we can write this as C1 integration of, so it's a definite integral, okay. So it's a basically, if we integrate this and whatever function you get, you put limits, so it's basically equivalent to having a definite integral of this thing from 0 to infinity. From 0 to infinity, e to the power minus eta square d eta equals to 1. Or we can write from here C1 equals to 1 by integration 0 to infinity e to the power minus eta square d eta. So that gives us C1. And now why C2 was 0? C2 we can set 0 from condition 1, that say limit, okay, we can solve C2 as well, but C2 will come to 0. The easiest and rough way to set C2 0 is the following. So first thing, that we know that at eta equals to 0, we say 0 equals to C1 integration of, so we put the limit here itself, so e to the power eta square is e to the power 0, 1, we remain d eta and plus C2. So if we integrate this, we can keep the limit here also. So limit eta goes to 0, C1 eta plus C2, limit eta tends to 0. So this becomes 0 plus C2. That gives C2 equals to 0. So that's how I get C2 equals to 0, and that's how I evaluate C1. Okay. So now once I get C1, so I can write theta equals to, integration of e to the power minus eta square d eta divided by integration of 0 to infinity e to the power minus eta square d eta. And we also know that this function e to the power minus eta square d eta, this function at the limit eta equals to 0 is 0, that we have checked here. So this is actually written in a slightly different form. So this theta is written as integration of 0 to eta with a dummy function e to the power minus u square du divided by integration of 0 to infinity. This again I can replace this with any dummy variable e to the power minus u square du. That's how this function is written. And there is a reason why we write in this way, because this is a well-known function. This is called Gaussian integral or of error function. Okay, this is a well-known function in mathematics. This is called error function. Any question till this point? A little bit of messy algebra here, but I think with your knowledge of maths 1 and maths 2, you will be understand that how we just make this definite integral and all other things. Nothing to do with heat transfer till and this towards the end. All we did is a little bit of mathematical juggling. Look at the board or whatever you call it, so and make sure that you understand the steps. C1, C2 evaluation, I think that is fine. So just let me first take this till C1, C2 evaluation. Till C1, C2 evaluation, everyone is okay?
Yes, sir.
Yes, sir.
Okay, good. So after C1, C2 evaluation, what I did is I just substitute C1. This step should be fine. This step is a little bit, I jump couple of things here. So it's easier if we go back from here. So suppose we go back from here and see whether we get this thing from this thing. So suppose we integrate this. So the to the power minus u square, say this gives us a function of g. So now we have to evaluate g at limit u goes to eta minus limit g u goes to 0. And we already know that this actually goes to 0. So it's actually the function just u and eta are replaced. So that's why we get back this thing. So just convince yourself that you get from here to here. You should be able to do that with your knowledge of maths 1, 2, whatever you have done so far. So now let us make clear that theta is given by this function. See, we could left it here, so we already got the solution. Although this integral has to be evaluated, and this is not easy because it's Gaussian integral. So that's why we take help of a function already available. Numerically, people evaluated that. So that's why we need to write it in the standard form. So this itself is also error function. There's nothing wrong with calling this error function, but we just make a little manipulation by calling, writing is a standard form, and we have designated as error function of eta. Clear? Now what is error function I will show you, but are you familiar with error function? Have you used error function before?
Yes.
Yes.
So you know error function, right? So you have used error function table. So you are familiar with error function. So it's a simple. The theta is just error function of eta. You see that such an incredibly simple solution. Okay. Now time for 5 minutes break, and then we'll solve a question. Use that break hour to ask questions if you want. So it's now 12:21. So we'll start at 12:25, 26. Just 5-10 minutes. Maybe 12:30 we can start. 12:30 we'll start. Okay, so let us be back. So you'll find error function table in back of your textbook. Let me see. We'll solve the problem so that you need the error function table. In appendix you will find. Yeah, you see that 1015, page number 1015 of 7th edition, you will find the Gaussian error function. Okay. So now you are ready to solve question. So I think that is in tutorial 2. Last question of tutorial 2. A rocky patch of earth was experiencing surrounding temperature 25 degrees centigrade for many decades. Fluid experiences keep change to 0 degrees centigrade. At certain time, a measuring probe measures 0 degrees centigrade 6,000 feet. Temperature will be 0 degrees centigrade 12,000 feet in 90 days. I think it has changed. I think I changed this one. Files. Okay, I think I changed this last question, so just hold on, I'll give you this on screen. Okay, I think I made some small changes, which is vital. So, yeah. I think I simplified this. Okay, now we'll see that. Okay, you can see the question?
Yes, sir.
Okay, now solve it using the error function table. So what is the value of eta? So post the value of eta in the chat box. Varun, check your values. Abhishek Purohit, your value is matching here. Abhishek Purohit is okay. Snehabandu Singh okay. Varun need to check. Yeah, Sam Jade fine. Yeah, fine. Varun Balkrishna, what happened? You change, correct the value and post it. Okay. So once you get the value of eta correct, eta should come something around 0.2268, and then your next step is to get theta, because theta is error function of eta. Since you know eta, now you can get theta. Oh, so plan needs to be made. I forgot. So it's basically plan is simple. Eta is given because Z and T are given, and temperature is being asked. So from eta is you know that theta is error function of eta. So get eta, get theta, from theta get T. That's the plan. Okay. So eta is 0.2268, and now what is theta?
Excuse me,
Yeah.
sir, could you please tell again the page number on which the table of error function is given?
It's 1015, Appendix B.
Okay, sir.
Mathematical relations and functions. And in some editions, the older edition of book I have, there is complementary error function is given, there is 1 minus error function. So you have to make 1 minus that value. Just check carefully whether whichever book you are looking, whether it is an error function or complementary error function.
Okay, sir.
Okay, sir. Yeah, Saskar Singh correct. Tanmay okay. Songs are they fine. Yeah, Snehavan the same correct temperature. Okay, all right. So that basically completes our conduction part. We'll have a conduction class test on next week. That is on 26th, and then we'll start on radiation.
Sir, in the table, values are given 2 and 1. So can we to a point interpolate?
You can interpolate. Yeah, 0.2 gap it's given. 0.02. Just linear interpolate should not be a problem. Okay, all right. So I think the temperature is coming correct for most of you. So if you have question, feel free to ask. If you don't have, feel free to leave.
So we have
26th.
so after that,
Radiation will start.
okay, sir. Okay, sir.
Excuse me. Sir, I have a doubt in last class, sir. Sir, the question which you discussed, sir, the one in which the plates were moving at the speed of 4 centimeter per second.
I think this network is giving trouble. Just type that in your.
Okay, sir.
Okay. Or you can call me. Problem 4 which you discussed in the class, how to calculate Biot number. We need to have height of the plate for that purpose. Not height, the depth, the width of the plate. The characteristic length for the plate is the width of the half of the width of the plate has to be used in Biot number. Okay, Abhishek, this answers your question? Okay. Height of the plate, length of the cylinder, those are not needed for Biot number calculation. The heat travel along the width of the plate, heat travel along the radius of the cylinder. So those are the characteristic length scale for Biot number calculation.
Sir, why we take half of the width of the plate?
Because that is the length which heat needs to travel. See, suppose you imagine yourself in a room where you have a door open in left side and right side. So if you are near to the right side door, you will not travel the entire distance to go to the left side door. You will escape through the nearest door. So that's why when the plate is pulled from both sides, half of the plate width is the characteristic length. If it's cooled from only one side with another side insulated, then the entire width has to be taken as the characteristic length. Characteristic length is the length which the heat has to travel before leaving the plate. That is half of the width. Alright?
Okay, sir.
Okay, sir.
Okay, sir. Thank you, sir.
Thank you, sir.
Okay, I think there is no more questions, so I am closing the meeting.